Hey everyone, yeah, I think we are online. Let's refresh that for the note. I'll give it a moment for people to jump in if they need to, and I'll probably also check the comments tab a couple of times during the session. But yeah, so I'm gonna jump into the code pretty quickly. It's going to be we're going to sort of explore the theoretical part of this as we work on the implementation. So the thing I wanted to tackle today is we're back to our BLE application that's based on the I don't even have the board on my desk yet. That's based on the NRF 52840 dongle. And we have a BLE application on this board, and basically what this BLE application does is it sits there and it waits for you to sort of do some commands. Let me hook it up and see if we can run it. It has a temperature sensor, and inside, so what happens is it updates the temperature every 2 seconds. And then basically from your peripheral application, you should be able to do this. From your peripheral application, you should be able to. No. From your central application, you should be able to. Screen. Yeah, but I want ACM0. ACM0. Yeah, something like that. Okay, cool. So yeah, as you can see, it's on, and then basically what happens is it's running some audio capture and such, and then in that, basically, if I go into my Bluetooth application, I can connect to a temp and light application. I'll connect to that, and then hopefully we should see a notification there about me reading temperature from the central device. So if I press read on here, we should see something like temperature read from central somewhere. I'll try and keep it read. Yeah, tempo's read by central. So you have a central application, and it can use BLE, and it can reach into this application and sort of fetch updates from it using that. Eventually, we'll do a notification from the BLE board back to the central application, and that's when we finish the audio recognition stuff that actually recognizes audio and sends it back to the application. So for now, I think the best thing to do is just jump into this code and see what we want to do. Okay. So not that for sure, and then I like putting this one on this side, and then in here I have the code, and then here I do have this is like my stream schedule, but that's not what matters right now. And here I will have activate. Cool. So I'll run the Zephyr virtual environment and that. Okay, so what are we doing today? We're adding a finite state machine to our application. And you usually need finite state machines when a system has distinct modes and or states that it can be in. And also this system, as it is in those states, it needs to respond asynchronously. It needs to respond not in order. It needs to respond to events in a way that is deterministic. And determinism becomes really deterministic means when something happens, you can predict or determine what will happen as a result of that. In embedded, this is kind of important, and especially when you deal with like safety conscious or security conscious things. Basically, you need to be able to deterministically, or you need to be able to determine which state you are in or you can't be in, because sometimes people's lives and people's businesses depends on the software that you're building and the hardware that you're building. So it becomes really important to have a very deterministic app that can tell where it's going and where it's coming from. So There is notes on this, and they're on that link, and this link is also in the video description, so you can go and open it and read it. But what I'm going to jump to today is I'm going to jump straight to the implementation. So maybe let's just look at maybe 5 minutes. I'll do 5 minutes. We just explore state machines for 5 minutes, and then we just go into the code, because I don't want this to become so theory heavy, which I enjoy very much, but I want to do some code today. So state machines are like, what are they? Let's go here. So yeah, everything looks like a neuron these days to me, but that's cool. So a finite state machine, or a finite state automaton, is simply a state machine that is a mathematical model of computation. If X, Y, if Y, Z, if Z, A, if A, B. That's really it. Basically, what this does is it determines a number of states, or you develop a number of states, and then your application could be in any of the states. And then what you need to do is to do responses to those states, to events in those states. I think there was a really good example somewhere down here. Yeah, a turnstile. So assume you're going to the railway and you need to cross a turnstile that needs a coin. So the turnstile could be in a number of states, which is locked and unlocked. Okay, if you walk to the turnstile and you find it locked and you try and push it, push is an event. If you try and push it, it won't budge. It will just go back to locked. Okay, it'll just stay in locked basically. Okay. However, if you walk to the turnstile and it's locked and you present it with a coin, it moves from locked to unlocked, and then you can walk through. Okay. But then let's start with the other side. If you walk to a turnstile and it's unlocked, someone put in money and then did not go through, and you find it luckily like that, what happens? If you push it, it's open, you can go through. But once you walk through, it will move. It will now be locked. You can't push it again. Okay. If you walk to a turnstile and it's unlocked, and you put a coin, you didn't know it was unlocked, you put in another coin because you want to go through, you put in another coin. If you push it, if you put in a coin, if the event is accepting a coin, it still cycles back. It cycles and stays in unlocked. And then once someone pushes it and walks through, it goes to locked. So the two states are here in this application, in this example we have, are unlocked and locked. And then the events we have is push and present coin. And basically you can see there's a little arrow here, there's a little dark arrow here, like a flowchart beginning arrow, and that ideally shows you the initial state of this thing. Okay, cool. I will breathe for a couple of minutes for questions while I transition into here so that we can look at this. Let's look at this. Okay. Any questions so far? Okay, cool. No questions so far. Cool. If you guys have questions, please ask them. So let's now go back to our BLE application and try and think about it in terms of state machines. So the BLE application has, and these are really very rudimentary states, but I kind of want to start at a very rudimentary point, because I want to put in the state machine and I want to ensure it's working, and then I can start actually making all the states that I'm going to be presented with, because I don't want to mix the implementation of the state machine and the implementation of the states themselves. So I want to put in a state machine, make sure it's working, and then once it's working, I can now start actually going into the minutiae and breaking down and building up and saying, what is it that in this state machine, what states do I actually have? Do states have parents? Do states have children? Does this? So I don't want to make a complicated state machine and then use that complicated state machine to build a state, to build a finite state machine. Okay, if that makes any sense to anyone. So let's start. So the potential states we will start with in the rudimentary implementation of this thing is we can have an idle state. So BLE is disconnected, sensors are inactive. So basically, the system has not initialized. And then we have a connected state where BLE is initialized, and I think connected. We can't do connected. It's a bit. It's a little. It's a little kind of iffy, because are we doing with initialization or connection? And it feels like connection. Maybe we need initialization, and then below that we have a child process which is connection. But we can get to that later. But for now, we'll have a connected state, which is when it's initialized. Okay, so maybe I should have called this initialized. And then we will have a temperature sensor reading in progress, mic capture active, and then we'll have an error state. And I'll show you all of these states. So let's jump into the code and just look at the source. So in our main, we do this thing down here, where we initialize the BLE service, we initialize the sensor temp service, and then we initialize the audio service. But so whenever we want to deem it connected, this action has to occur. BLE service C. So in here, whenever right now we're going to assume whenever Bluetooth is ready, we are connected, basically. But if we were clever about it, what we would do is we would wait until someone has joined. Okay, someone has actually joined our Bluetooth network, and that would entail adding a callback so that we can be told by the Bluetooth subsystem that someone has joined. Okay, so whenever Bluetooth is initialized, we will go to the connected state. Okay, and then whenever the temperature sensor is initialized, not actually initialized, whenever the temperature service is reading, so initialization won't matter, and then whenever it's fetching the temperature, we will go into temp read state. So it is reading the temperature. The thing is reading the temperature. That will become the state. Okay. And then in the audio service, whenever the audio service is sensing, it's that 2 seconds. You remember, if you recall, our app goes, whenever it's doing this, it's sensing audio. We need to be changing the states. So as you can see, the app can be in several disparate states that are in different places in the application. And in order for you to connect the logic of how everything is working, say you are starting to also develop on this machine, on this app, or you're trying to jump into this code, it becomes very difficult because the entry point looks like very simple. This application's entry point looks So this application's entry point looks very simple. The main has 3 calls. That's it. But really, there's a lot of things that are happening in the background, and you need to be aware of these things so that you can actually handle them the way they should be handled, if I may say that. Okay. So what we want is to implement a state machine that accounts for all of the states that we could be in, and asynchronously helps us to respond to events. And that way we have a way to determine if Y happens while the app is in state X, what is going to be the response of the app. Because what we want to do is basically I want to remove this from it. We want to be able to tell what will happen in the application. And this is important, especially when it comes to certification and things like that. So I'll remove this here. I'll do WPF, and then I'll do audio service, and then here, audio service. Audio service, and then in here I'll go. Yeah, that's fine. So we don't need the other one as well. So that's cool. So we do have a logger somewhere here. Okay, cool. we've done 5 minutes of the thing, so let's actually now go into some sort of implementation. And we can look at this for flowchart. So we start, we initialize, we go straight into the idle state, and then BLE is initialized, we go into the connected state, and then from the connected state we can go to mic data ready, temp data ready, and all of these states can always error out, and there's arrows going all the way to the error. Yeah. And basically, if we're clever about it, we can do something really clever. If all of this data only matters when someone is connected to the BLE application, then some of these actions, we don't need to take them. And this becomes that thing I was talking about, a low power application, where we know someone's not connected, so we don't need to go and fetch this sort of computation because no one's going to use it. We're not in a state that is connected. No one needs to know anything because we anyways discussed this data. So we can't stop services. We cannot advance into actions and just sleep until some state is achieved. And those are the things that are kind of end up becoming power savings and so on and so forth. So we can't know when the app is where, and it aids us in power saving. It aids us in knowing what is happening. There's so many benefits to modeling your application as finite state machine. So that's that. Let's look at how to do this in Zephyr. So Zephyr has a framework, and it's called, we actually can start from the beginning. So Zephyr has something that's called state machine framework. And the state machine framework is an application agnostic framework that provides an easy way for developers to integrate state machines into their application. So traditionally, the way I've done this before is you actually implement the code for your state machine in your code. So you build a state machine along with your code, and then you kind of do stuff with it. Or you even implicitly build a state machine where you maintain some struct somewhere or some map of stuff, or some enum, and you're changing which state is in which. So you could implicitly do it or you could explicitly do it. So it depends. But let's look at how Zephyr does it, because this is good. It's always nice. I was thinking yesterday, and I realized you don't really need to. Summer's coming if this flies. You don't really need to do something amazing to stand out. You might as well just learn something that works. Learn something good. Instead of going out and building your own operating system, go and learn how Linux works really well. Because Linux is a good operating system. Windows is a good operating system. macOS is a good, whatever, whichever one you go. Go learn how a good operating system works. And then you'll have this, you can build this intuition of how to actually implement this thing later, because later a chance might come up and you would want this. So, kind of a segue, but yeah. Fix stuff that exists. There's a lot of nice problems that already exist. You don't have to invent your own. You don't have to suffer from the not invented here syndrome. Speaking as someone who's suffered that for quite a while. Okay, so let's jump into this. How Zephyr does this. So this framework can be added to any project using the kconfig SMF option. And then you can create individual states by a state is represented by 3 functions. We have one function implements the entry actions, another action implements the run action, and the last function implements the exit actions. So when you get into this state, this is what happens. When you're in this state, this is what happens. When you leave this state, this is what happens. It's like kind of like a preamble, a postamble, and an amble, so sort of thing. And then this is how it looks like. This framework uses the SMF context framework, and you need to make an object or struct that you pass to the framework, and then in the struct your SMF context has to be the first one because the thing casts, I guess, and then when it casts that, it will use the first memory address to pull the stuff. And by default, a state can have no ancestor states, which results in a flat state machine, which means states don't have child states or parent states. But you can enable this later. And the return value of the run action is the SMF state result. and then determines if the state machine propagates the event to parent run actions or if the event was handled by a, yeah, cool. Flat state machines do not have parent actions, so the return code is ignored. Returning SMF event handled is recommended. Okay, cool. So we're going to focus on being in a flat state machine because that's the initial simple one. And then later, like I said, we're going to make it more complicated. But right now, let's put a framework in. Let's get it working, and then later we can go there. Actually, let's jump into the code. Let's see. So the first thing we need to do is convene SMF. So let's do that. Let's go to kconfig. I'm going to here. Yeah. Okay. Let's go in there. What I just did was just delete something we were not using. Oh, wow. This config is becoming insane. It's becoming an actual production config. Okay, cool. SMF options. State machine options. Machine configs. So the first thing we need to do is to do config SMF. Config SMF equals, yeah. So that's the first part, and then if we go to, yeah, I can do it somewhere here. Search kconfig. In the meanwhile, as that loads, does anyone have any questions? I'll just start doing this. Okay. No questions so far? Config SMF. Hierarchical state machine. This option enables a hierarchical state machine. Cool. So we've enabled the state machine. That's it. So that's the first thing we need to do. And then we need to create states, I think. Yeah. So the states, you remember the states we looked at just now. So the states, yeah, error state, idle state, might capture state, temporary state, connected state. Yeah, so that we need to add those. And then all of these are events that cause the states. So let's just add the states first. So let's go down this and see where we can get the states. Yeah, and instead of doing this by hand, we can always use this macro SMFCTX to construct it. I like this one better because it does it for me, and I don't need it. Yeah. And by default, a state can have no ancestor states, resulting in a flat state machine. But to enable the creation of hierarchical state machine, SMF ancestor support, I've seen it somewhere here, ancestor support. Yeah, you see. The state machine will include ancestor state support. We will do that later. For today, we're just implementing the normal state machine, a flat state machine. Okay, cool. So, for example, no, we don't need that. A return value of the run action determines if the state, yeah, we've already read that. Calling SMF state, set state prevents calling parent actions. That doesn't matter to us right now. By default, the hierarchical state machines do not support initial transitions to child states on entering a super state. To enable them, yeah, so that's fine. And the following macros can be used for easy state creation. SMF state create. Okay, cool. So let's actually let's do some of this. I think we can do quite a bit of this in main, and then we will move this to its own thread later. So source and then main. Let's do it in main. And I think there's quite a non-contrived example somewhere down here that we can follow. Actually, let's just follow this, and then we can see if we need something, we'll go back up and stuff. Since there's an example and we want to do that. So let's include the Zephyr SMF in our application. Okay, I'll add a space there just to include Zephyr SMF.h. Okay, cool, that's fine. We've added that, and then let's come in here and we can say state machine work. I'm just commenting it in so that once we are done with it and we want to move this to its own thread, we just have an easy time. State end state machine defs, so that we can move it to its own thread and we can go back to a nice clean entry point. So let's first of all, let's do the first thing. Enum demo states. Okay. Enum BLE app states, and then in here we're going to do to say we know our states. Actually, we know our states. Idle, connected. Okay. Idle, connected, and then I think it's temp read, and then I think it's my capture, and then I think it's error. So those are the possible states. We've added the states. Okay, so that's fine. That's the first part. We've added the states. So let's go to the next part, and then user defined object. Struct state object. Let's do struct state object. I don't like calling it a state object, but that's fine. And I think in here we need to include struct SMF context. Struct SMF context CTX. What do we call it? CTX. State context. It's just the same thing. You can call it whatever you want. So there's that. Let's do that. So we've added that, and then I think we need to terminate that. So we've added that, and then we need to make entries. Entry for state 0, run state result for state 0, and an exit. So 3 functions per state. Do I want to copy this? I can copy it. It's not a problem. Copy it. Okay, cool. Should free. Okay, cool. So this is, let's look at it this way. This is, see, like that. You can say idle entry. You want to do something when idle is entered, and then you want to do idle run, and then you want to do something when idle is exited. Okay, and then here instead ofsobj we want state object, I think, and sobj and state object. Yeah. State object, and I think demo state is BLE app state S1. BLE app. Why is it not gonna? And then instead of S1 we want idle. I think that's it. And that's it. So this, basically what we've done here is we've made So we have an entry function. Remember, an entry function works when we enter a state. It's run into when we enter a state, and then a run function is when we are in the state, and then an exit function is when we leave the state. So that's fine. So we basically need You're joking. I'm confused. They are defined. Oh, okay, cool. So this needs it's a type def basically. State object. So there's that. do need to declare the state table here first. So static const struct SMF state BLE app state demo states BLE app states okay, BLE app states. So there's that, and then we want enum demonstrate BLE app state. So enum is just one of them, and then the collection is BLE app states. So enum app states. So this is just one. That's fine. Just stay. I'm not gonna do that. Okay, cool. So that fixed our errors. What we've done here is we've made the state table, isn't it? Yeah, the state table contains all the states that we're going to be using, and then we've listed the states that we need in our application, and then we've defined a state object. Well, let's look back at the core, so we know what the state object is. A state is represented by three functions, where one function implements the entry action, another function implements the run action, and the last function implements the exit action. The prototype for the entry and the exit function are as follows: void function, void object. That's fine. And the prototype for the run action it returns an enum. There you go. It returns an enum of which state you're in. So this tells us that we've transitioned state. And where the object parameter is a user-defined structure that has a state machine context there. Okay, cool. So what did we want to do? What is it that we wanted to find out? So we know this is what is going to be used when this returns. Yeah, this will return a state result. So enum state, SMF state result. And then this will return that, because in flat states, it doesn't matter. Cool. We could actually do things like log. Let me just put some logs so that this function is actually log one entered idle. And then let's do that. And then here, let's do log one left idle. So let me see if I understand this correctly, and then we can do some questions. So I've made a state table. State table holds all the states that are possible in the application. I have listed the possible states inside the enum of app state. And then I've made a state object that I'm going to be passing through all my states, all my state functions. Yeah. And then this is going to be used to return the correct state. Yeah, so I've made this state object here, and this is going to be passed into the run functions, and then it's going to be used to set state. This set state. So SMF set state. Do you want to know what that does? SMF set state. I think it just calling SMF set state prevents calling parent actions. I don't want to know what it. I don't want to know that, but I want to know what it does. It changes a state machine state. Try saying that. It changes a state machine's state. That's a mouthful. So this, so this changes the state machine and into that. Basically, that's what happens here. Okay, so we have that one for the idle, and we need one for, let's keep going. We need one for connected. Why? Oh my word, I wish I was cool and I could do this connected. Yeah, it will be nice when this moves to its own translation unit. But for now, I'm gonna keep it all here, although we will end up with a 300 line main SP. And then here, I don't want idle entry, I want connected entry. Connected entry. I can see why that it helps to write code that is sort of self-reading, so that's fine. This one is going to idle, and instead of idle here, I will have connected. And then in here, that I won't do anything, and I'll say left connected. Left connected. Okay. And then in here, I'm going to add another one for which is the other state, temp read, and then I will do SP, and then I'll say no. That is actually thank you so much. I am connected. You know what I'm gonna do later today? I'm gonna learn how to do like arranged find and replace. Then I can do all of this very quickly, so I don't need to go line by line. But I kind of sort of like going line by line, because then I understand the things I do. So I'm gonna say this is temp read. I'll just name it temp read. Okay, and then I will go back here and I'll call it this. I'll call this one temp read. I should have chosen less states to start with, but it's fine. And then I think this will be temp, and then I think this will be temp read. Left temp read. Okay, cool. So that's temp read. How many more states? And then there's mic capture and error. Let's do mic capture and error. So mic capture. It's fine. So this is mic capture. That does nothing. Entered mic capture. And then I think we want to do here, instead of idle here, we want to go to mic capture. And then in here, this should be a mic capture run. Okay, and then I think here, this is mic capture exit. I like that the apps are like void nothings, so you can actually pass in whatever you want and use it however way you want. So that's cool, which means you can make quite a non-contrived state machine. You can really operate between the states, and you can set things, do stuff, and all of that stuff. Maybe not. Maybe it needs to be like some sort of no side effects thing. I don't know yet. Left mic capture. And then we want the last one, so we want to know error state. Okay, so let's remove that, and then I think excuse me, I just need to think a little. So this is error entry, enter error. Okay, and then here we want to actually transition, let's say error run, and then in here we want to transition into error. And then it's funny to want to transition into error, but that's fine. I'm gonna be done with this part soon. So if anyone has any questions, I'm gonna pause and look at the YouTube thing so that we can look at it. So please, if you have questions, I'll pause as well and look at what's up. So let's look at it. This looks like it kind of looks okay. So we have functions. We have entry, run, and exit functions for all our states, all our 4 states. So idle, connected, temporary, mic capture, and error. Okay, cool. Taking a break, sipping some tea, checking on questions. Does anyone have any question right now? I think. Any questions today as we handle this? Let's check what's up. Okay. No much. No questions. Either I'm very good at explaining, or hey, thank you. Hey, Zoom. Zoom. Did I say your name right? Zoom. Hey, Zoom. Nice question, Brian. The run states are actually transition states. Check this. So I just looked at that now. The run states are transition. So remember, in the run function. So in the run function, I'll do some questions and more just now. Neovim, and you can tell it's Neovim. Okay, cool. I feel like a cheater using Neovim. Brian, I'm back to you. Let's do your question. Why? Brian just asked, why do the run functions return enums? So remember when we were looking at the code here, and it said each function needs all of this. A state is represented by 3 functions, where one function implements the entry action, another function implements the run action. So the run action actually transitions. Look at it this way. So in our SMF state set state results, which is our run action, we call SMF set state. If you go and look at the documentation for SMF set state, it changes the state in a machine. So it doesn't really return an enum, it just sets our machine to the specific state that we want to. So this doesn't have to be like done immediately. You could do computation here to determine if you want to be here or not, or cause some side effect. It's kind of like you have a meta handler for your application, and then in this meta handler you can do stuff, and you basically know when it's moving from this state to that state, and then you can kind of move them about. That's why. Another question. Maybe one day I should make a live about how I use Neovim. I'm not gonna even lie to. I'm not even gonna lie about this. If you wanna use Neovim like me, you wanna do the YouTube. Don't wanna do YouTube, which goes YouTube. I don't know. Let's see what it shows up. So my YouTube's basically blank because I don't have. Yeah. By the way, there's this plugin called Unhook. It removes YouTube shorts and YouTube suggestions from your feed, so your YouTube looks like this, and then you don't get to like binge stuff. But Neovim from scratch. There's this video by the Parmesan from 2 years ago. This is what I used to move from. Vim to Neovim. Go use that if you want to use Neovim like me. You use that, and then I do have GitHub. We're going back to Zephyr just now. GitHub's, but I like it when people talk to me, so I'll answer them. GitHub Zach, and then I do have Neovim. I have Neovim what is it? I have my thing committed, and you can go look through here. And if you want to set up your plugins and all of that stuff, you can look through here and you can file issues and stuff and whatever. But basically, you can look through this, and I have all the explanations of how I use them and everything, and it's cool. And it gets really cool. Anyways. Brian, why are you laughing? Let's go back. Let's go back and do some Zephyr. I'm actually really chuffed. This is the problem of having friends online, is that you stop doing the thing you're doing. Okay, cool. So I've answered Brian on why run returns an enum. It actually doesn't really return an enum. It just sets the state of the state machine. Yeah. And then I've answered the NeoVim question. So let's go back to the implementation that we're following. Okay, cool. So SMF state result, right? So S1, S2, S0, that's there. We've set our stuff. And then now we need to actually populate. Yeah, dude, blank YouTube. Save time. Think about it. If you opened YouTube, think about it. If you just open YouTube every day and it just looked like that, you'd be like, what am I doing here? What? Because I'm a streamer or whatever. I don't know if I'm a streamer. But what I'm saying is I stream. So I spend a lot of time on YouTube. Yeah. And if I let myself alone with YouTube, I'm going to end up spending the whole day on YouTube. Whereas I actually want to do code and do stuff. So when YouTube is like this, it just puts that one little blocker in the way. And I'm like, I have to search for something. And then if I have to search for something, what do I actually want to watch? Do I actually want to watch something? I don't care. I go back and I do code. That's really the story. But okay, cool. We're almost done. Look. We're almost in the main. So let's populate the state table. Okay, cool. So let's populate the state table. The state table now actually builds the... You remember we did a forward declaration at the top of the state table? Now we're actually going to put states in it. Okay? So let us actually do that. I feel like I want to copy this. Because I'm lazy, man. And someone way better at Zephyr already wrote it than me. So let's do it. Let's do it here. So make a state table. And a state table is just like a truth table. I know most of you know what truth tables are. A truth table is like, nah, man. Should I do that? Nah, I don't need to Google truth tables. A truth table tells you what if 00. It's like the times table. If you're Kenyan and you know at the back of the book there was always times tables, but I don't know if that's a thing these days. Maybe I'm showing my age. Should be. Let's go state table, and then instead of demo states we want BLE app states. Yeah, BLE app states. I think so. And then I'll remove these comments because we know what they are, and then I will make 4. Is it 4 or 5? How many do we have? How many states do we have? 4 or 5. 1, 2, 3, 4, 5. So 5. I'll just come here and see. No. I'm actually, don't tell this to like the people who taught me how to use Vim. Bernard, I'm looking at you. Henry, I'm looking at you. I'm actually pretty bad at using Vim because I use the mouse. Alan Oth, I'm looking at you. Please do not judge me. The people who taught me to use Vim would be so ashamed. First of all, that I'm using NeoVim. Second of all, that I use the mouse to move around and stuff. But anyways, life is as such. So even you people who think whatever, it's cool. So the first state is idle. And then the second state is connected. That's you. Yeah. And then the third state is going to be temp. Right? And then the fourth state is going to be mic. Right? And then the fifth state is going to be error. Okay, cool. And then in here, let's actually complete them. So entry. So this is going to be idle idle, and why? No, I don't want to do that. It's fine. I want to call them like this. So idle run, and then idle exit. These two nulls is the parent and the default. When we get to hierarchical states, we'll deal with them. But right now we're not dealing with them. So I don't want to do a null here because I don't know why this one is null. Why is this one null? Oh, okay. It can basically not have an entry action. It's just there to, yeah, let's actually do it. We don't have to connected run. Eventually we'll change it. Connected exit, but it might complain to me about not using that function. So maybe temp read, yeah, and then I want temp read. Yeah, YouTube is also just an app that was made by a developer like you. Don't spend all your time on someone's app. Do stuff. Same as Instagram. Same as you see. All those developers whose apps you're using, they don't know about the apps you have. They don't know about like the other apps. Remember, save your time. Life is made of time. Use your time. Don't give it away. Error. Error. I mean, this is just demonstrate, but I don't want to get warnings about those functions that I've defined and then be told I'm not using them. We can actually just I will ignore it. Yeah, let's remove them. So this is an exit. I want to remove the connected entry so that we're not using it. Yeah, I want to also remove temperature exit because I guess we're not using it. Are we using it? Nah. You know what? I want this code to be simple. Because it's still in the main file. Once it goes to its own translation unit or to its own module or its class, whatever way you call things like that, then we can make it like big and fully fledged. For now, I just want it to be like really small and compact so that it can show how this thing up. Okay, so let's see. We've made a state table at the end of this all. We made a state table. So the last thing we need to do is what? I think we've kind of achieved it. Whoa! We've achieved it. We've done it. It's not running yet, but we've done it. We've built a state machine using Zephyr's state machine framework. This is cool. So let's look at it. Run the state machine. So let's set the initial state. Ooh. Okay, cool. So let's set the initial state here before the app connects. Before we even run. I love this, man. Okay. Is SMF set initial state? SMF set. No. And then in here we will take a struct, and instead of taking a struct, I'm gonna construct a struct using this macro SMF ctx, and then this takes an address, yeah, and state object, yeah, and then the next part is the demo states, and then in here I want to pass in the demo states and BLE app states. Okay, cool. Okay, I'm getting to almost the hour of streaming, and I know people have work, and while this is enjoyable, I'm gonna stop now soon. Okay, cool. Let's see. BLE app states, and I want to choose the. Come on, it wants one. I want to see if it builds, and then if it builds, I just want to see if it works, and then if it works, we just stop there because we've learned what it does, and then we can do it. Tomorrow we'll pull this into its own application. Tomorrow we can pull this into its own thread, and then once we have it in its own thread, what we can't do then is start becoming very explicit with our states and actually doing the transitions and so on and so forth. Because in any case, the way it's done, you want to use a message queue. So you want to make a message queue. You don't want to. Let me show you where I saw that. Come on, give me my mouse back. So I'll show you somewhere here. Your threads cannot actually call SMF set state. Your threads cannot actually call SMF set state. Okay, not that one. I want another one. Yeah. While the state machine is running, SMF set state should only be called from the entry or run function. Calling SMF set state from exit functions will generate a warning in the... Oh, no, that's not the thing I want. Basically, we can't just call set state from anywhere. Okay? And what that means is we need to use, I think, where did I read this? I forget where I learned that, but we can't just call set state from anywhere. So we don't want to go into our, let me show you how this works. So we don't want to go into our audio service, okay? And then in our audio service, whenever we start sensing audio, we don't want to set state mic capture. We don't want to do it here. That's kind of, you're now just throwing it about. You want to put all of this in one place. And the way I want to do it is I want to make a state thread, and this thread transitions states, and then we can have a message queue somewhere where this actual threads call out to that message queue. And when they call out to that message queue in turn engages. We've done this before. Whenever we were doing the temperature service, we made a message queue somewhere. If I'm not wrong. Yeah. So you see, there's a message queue. This is a message queue, but I think it's in main. And this is why I want to move this out of main. You can't see now because I've added so much code in here, it's hard to see. But we define a message queue for temperature. And whenever the temperature service actually reads something, it doesn't tell anyone. What it does, it just puts into that message queue. Yo, Brian, check this. Check this cache invalidation. I just throw away the last item. I don't do LRU or anything. I just throw throw away. This is too old. It's expired. Throw it away. You guys and your complicated algorithms. I don't know. Anyways, cool. I'm making fun of people in the group. This is quite cool. So what was I explaining? We're going to implement a state message queue, and then that message queue from our threads, we're going to post to that message queue, and then we'll have a state machine thread, and that can consume from that message queue. If that makes any sense. Do we have any questions? I'm going to start running this application just so we can check whether it worked. West build. We're coming to the top of the hour of streaming, so I'm going to stop soon, but I'm going to west build -b. Oh, I don't remember this one. Control R, NRF. Yeah, I don't remember it all like the STM32F4. I should NRF 52840 dongles / promising I will. OBS is saying it's disconnected. Yep, so that's back. Let's see. Building this. Basically, if it builds, it means we have everything. And I think all I want to see is that first log entering idle. That's all I want to see. Then I know our state machine is working. and then I can move it to its own thread. Then I can move it somewhere else and can start working on it before, make it work, make it good, then make it fast. Okay. Do the necessary, then do the possible, then suddenly you'll be able to do the impossible. Start with what is necessary. What is necessary here is making it work. I need to get an ARM machine so that Zephyr builds faster. Oh my word, it built! This is cool. Build Zephyr.config. I just want to see if actually it's there, and then I will grab in here. I want to grab, what do I want to grab? SMF. Oh, yeah, look at it. We have SMF in the build. Cool. So let's actually explode it out and do packet. Control R, and the thing is dash hardware. Yeah, this packet. And packet here is making a zip with our thing, and I always do this because this microcontroller does not have an onboard debugger, so we need to use the onboard bootloader. So we want to make a zip, and then we want to give this to our bootloader. And then as usual, I'll do it once in the stream. I'll put it in bootloader mode, and you do that by pressing the button here. It goes red, and when that goes red, you will notice this disappears. Okay, cool. And then we will do Control R and then DFU, and then I will just load the executable into the board. And then once that's done, I want to start the log here and see what happens. Entered idle. Wow. Shit, how do I do that? I just want to do it again. I want to push up, do this. You'll see it here. No. I don't want that. Push up, do this. And then 1, 2, 3. 1, 2, boom. No. I should have disabled logs. I can actually just comment out the lines after that. Yeah, this is not actually. Yeah, custom entered idle. Do you see that? Yeah, we get entered idle. And there you go. And what we've done today is we've basically implemented a state machine. We haven't started using it, but we've actually put in a state machine into our application. And I'll put this up so that we can reuse it. Git checkout PR add state machine. Okay. Checkout -b git states git add prj git diff --staged git commit -m state machine activate SMF framework git status git add src main git diff --stage. I do just quickly skimming it just to make sure it's all sane and I didn't throw in some stuff I wasn't supposed to or breaking some stuff, and that's it. Git commit -m state machine initial state machine implementation git push. Of course it's gonna scream at me, and then I wanna copy that Put that up, and then I suspect if we go up, we shall find a PR here. Compare and pull request. This PR adds a state machine implementation to our application. Yeah, if any one of you wants to go and review this, go review it and we can get it. So all the code is up there. You can see the code that I added. You can find this link here. This link is also in the description. And what else? It's been amazing working with all of you. It's been amazing having people talking to me while I'm streaming. And this is cool. This is getting quite awesome. I'm having a lot of fun. Anyways, it's been amazing picking up and learning the Zephyr state machine framework and seeing how we can use it and putting it in an actual application where we're using it rather than just thinking about it in wishy-washy theory things. Thank you so much for everyone who came. Thank you so much for Zizang for all your questions and all your talking. Thank you, Brian, for being around and laughing at my blank YouTube. It really works. Yeah, thank you everyone for everyone who hung out and watched this through. Thank you so much and cheers. See you tomorrow. We'll do something cool. Amazing. Cheers, everyone.